Hey folks, welcome back. We are getting ourselves ready for exam 2, doing a review problem that I am calling all of the above. The physical system is that we have a hammer being raised up 1.2 meters and then dropped onto a piling that is 140 kilograms, so the 650 kilogram hammer is raised 1.2 meters, is dropped onto this piling, and when it is dropped, it is pressed into the ground 110 millimeters. The impact is perfectly plastic, and we are asked to find the average force resisting ground penetration, right? So the force preventing it from going further. And I call this all of the above because there are, it's got everything, right? It's got work, it's got impulse and impact, it's got conservation of energy. Great problem. And because it's a, excuse me, such a great problem, I thought this would be a good opportunity to highlight a couple of attack strategies for this. So I can think of two good attack strategies for solving this problem. And so the first I call the physics approach. And the way that that works is that I consider the very last thing that I'm asked. Right? It says, what is the average resistance to ground penetration? Right? So that means penetration, the ground penetration is an X value. Okay, well, what that tells me is that that is a work problem, right? So working backwards, we would have our work problem, right? And work is U1 to 2 is equal to T2 minus T1, right? In this case, T2 is going to be 0, right? Because it's coming to a stop. And this is what? This is Fx, right? And that is equal to T1. Well, let's see. What is Fx? Well, that we're going to do oh, gee, it's a free body diagram. Lost my words there. And we'll find that we've got weight up here, and we've got our force of interest down here, right? And depending on which direction we go, we're going to have these, and then we'll get that from our kinetic energy. Well, what is our kinetic energy? That is 1/2, and let's see, this will be both of these masses, so I'm just going to put m total, right? And then v1 squared. Okay, well, let's see, we're given this, we can get the weight, right? And so we need this v. Well, how are we going to get the v? Well, let's see. We're going to need impact, right? Because we know that the hammer is going to hit it, so impact, we can call it impact, we can call it impulse, because the impact values are going to be 0, so we can name it both, right? Impulse, okay. And the equation there is, let's see, we're going to have to be careful with this, right? So this will be mh, v, and we're going to have to go with a 0 here because we need that, and then plus whatever our impulse is. We're given that it's 0, but we can write it down. Let's see, this will be 0 to 1, and that's going to equal mt v1, right? This will be 0. Okay. So our input here is our output here. Now we need this, right? We need this v naught. Well, where do we get that? Well, let's see. We got to the impact. So how did we get to the impact? Well, we got there by dropping the thing, right? So that is conservation of energy. And I'm just going to say COE, right? And the equation there is T1 plus V1. Oh, wait, we need values here. Let's say Ti plus Vi equals T naught plus V naught, right? And when we raise something and drop it, it starts with no kinetic energy and it ends with no potential energy, right? So this would be our relationship and we're given the height, right? So we go from here to get the v naught. This is strange, right? Because this is going to be 1/2 mh v naught squared, right? Which is what we need here, right? So we go here, this gives us this, and there we get to there. So this is the physics approach, right? And it's just something you can do, only takes a second. Sometimes if you're comfortable with the material, you can do it in your head, right? So that is approach number one. The other approach is to think about physically what happens. Well, physically what happens is that we raise something up, we drop it, it drives something into the ground. So we can start just by drawing it out. We can call this position 0, right? And this is, at this point, we just have our hammer, right? And we're going to drop it to position 1, where it is going to have, where it's going to make an impact. Get it? Okay, so here we go. Okay, that is a handy dandy little symbol for I cut it off and I'm not going to draw it. So let's see, this is MH, whoops, MH, not HH. MH, okay, and this is MP, right? And I'm calling this 1. So as we do the calculations, we're going to do from 0 to 1 with the conservation of energy, and then from 1 to 2 with the impact, right? So I'm just going to go 1 to 2, and I can say COE here, right? And I'll just say IMP here, right? And then we're going to go down some distance x, right, which is going to give us position 3. And this is work, right? So I know now, just by thinking about where how the physical progression of the system works, I now know I'm going to go through these equations in this order. Note, it was much faster to use a graphic approach, and it tidied up my subscripts, but the physics approach gave me the exact equations I would need, right? So there's a trade-off, if you will. It's a little more abstract. I think to do the physics system or the physics approach, you need to have a little bit better understanding of how the equations work. And we could just as easily now go backwards, right? But we just did. So let's go forward. So we'll start with our conservation of energy. Okay, and our equation there. Now that we have subscripts, we'll use them. So T naught plus V naught equals T1 plus V1, right? And again, we start with no kinetic energy. We end with no potential energy, right? So what is V naught? V naught is MHG and H. And that's going to equal 1/2 mHv1 squared. The m's drop out, and V1 is equal to 2GH, which is super famous. Okay, so let's run that through the calculator. We're going to need the square root of that, aren't we? So the root of 2 times 9.81 times 1.2 gives us 4.852. So 4.852 meters per second. Okay. All right. What's next? The impulse and momentum, or impact. Either way. Let's see. I think if we have to pick one, it's better to call this the impulse and momentum. The reason is it reminds you that we're working with momentum, right? So what do we have? We have the number 1 position is MH V1 plus, I'm going to write this out, impulse 1 to 2 equals And after the impact, then it's both of them traveling, right? So now we need mh plus mp times v2, right? And we were given that this is a perfectly plastic impact, so this goes to 0. And v2 is just a scaling of v1, right? So v2 is, what is this? This is 650 over, and 650 plus 140 is 790. 790 times this, so times 4.852, and what does that equal? Let's see. That equals 3.992 meters per second, which makes sense, right? It slows down when it impacts that. All right, then we have work. Okay, and work is U1 to 2 is equal to T2 minus T1. And again, T2 is 0. So let's see. We have our thing we should draw, and we can do it this way. We'll draw it together again. Okay, and so I'm going to put M, well, we got going down, we got the weight, right? So I'm going to put MT, right? So for the total times gravity, and going up is our force of interest, right? And we need a direction to call positive. Let's call the down direction positive, because that is the work is being done in the positive direction here. So let's call that positive. So what is this? This is Fx. That is going to be equal to the initial kinetic energy, so minus 1/2, and this is mt for both of them, and then v2 squared. v2 squared, F, what is F? So if we have a sum of the forces in the positive direction, then that equals F minus, let's just say 790 G. Okay, so then we have F minus 790 G times X. What is X here? It is 0.11. 0.11 is equal to minus 1/2 m squared. Let's see. Yeah, I'll just calculate that. So minus 1/2 times 790 times this guy. Wait, not that guy. Different guy. That guy squared. Uh-oh, lost it. Hang on, gotta type that again. Okay, 790, and then 3.992 squared. Okay, and that is 6294.75 minus there. So then we divide it by 0.11 divided by 0.11. Okay, so then we get that F is equal to minus 57,225. For some reason I feel like I'm going backwards here. really think I am. I think that this was backwards. I'm sure of it. So let me do this. Go here, okay, and this just reverses the sign, right? So we're good, but it just reverses the sign. There we go. So then here, if we multiply everything by -1, then this ends up being 57,225 plus 790G, which makes more sense. So F then equals this plus 790 times 9.81, and that gives me 64.975 kilonewtons. There we go. Cool. So again, there's various approaches you can take to it, and I recommend just taking a minute and in one way or another working your way backwards, right? Because even when I was drawing the steps that the system would have to take, I'm still kind of working backwards. So at any rate, I hope that was helpful. I hope it helped you on the exam, and I will see you in the next video.